password. So in this case, by using the interrupt vector table, every complicated firmware image will automatically have its own sort of unique password. And the manufacturer will have a copy of that password, but no one else will. And the compiler can't not set the password. So when you have all of these fly-by-night, hey, let's make an MSP430 compiler companies, they all, by the very nature of the chip, have to make a unique password for each image. So to crack it, again, getting back to the timing, we need to stretch our timing for reasons that I'll explain in a bit. Specifically, if we send bytes which are the proper distance apart from one another, then the victim chip will wait for bytes. And so long as it's waiting for bytes, whatever timing variance might have existed has just been destroyed. Further, we need very low latency because we have to control exactly when the line falls, exactly when it rises. So the low latency is more than we can expect from a PC parallel port. And the solution is to use an MSP430 to attack an MSP430. So roughly, we're looking at 2 microseconds per correct or incorrect byte. So we need to sample at least 1 megahertz. If there were a context switch in a PC, that would destroy this information and we wouldn't find the solution. So quickly reviewing RS-232, it consists of marks, which are zeros, and spaces, which are ones. There's a start bit to indicate the beginning of a byte, and a stop bit to indicate the end of the byte. And in this case, we have a parity bit. So if you remember from your BBS days, when you would connect it to 8N1, that means 8 bits, no parity, 1 stop bit. And then 1 start bit is implied. So in this case, we're on 8E1, which is different from the BBS days, but there's a good reason for it. So each packet begins with a single start bit, then the least significant bit comes first. You work your way up to the most significant bit, and then you have a single even parity bit followed by a stop bit. So considering the example of 0x80, it begins by a fall to a mark. The mark lasts 1 space, and then we have spaces for the individual data. So this would be our least significant bit, which is a 0. Then we have another 0, another 0, and another 0. This is our least significant nibble. Following that, we have the 3 zeros of the more significant nibble. Following this, we have a 1. That's the 1 within the 8. Following that, we have another 1 to make the number of 1s within the message even. And then we have a single stop bit. Now, 0x80 is sent before any given command frame to the Bootstrap loader. Do any of you know why? For what?
Make it wake up?
Not quite. This is how it determines how quickly the transmission will be. The message looked, think of it as a difference between the 2 edges. If you divide that by 8, you get the width of 1 bit. So that's what it does. It tars its own time by measuring the difference between these 2 edges. And that's how it knows how quickly to speak to you. As long as you don't overrun or underrun this counter, you can choose any odd baud rate that you like. If you speak to it at 9600 baud, it works fine. 9605 works fine. 9700 works fine. And because of this, you can make it speak more quickly or more slowly than it's supposed to. To send 0x90, again, we have the less significant bits, followed by the 1. And then we have the most significant bit. That's the 8th bit in the 9 nibble. But here the parity bit is 0. If you look at these enough, it's easy to recognize the difference in a scope recording. Now, this is implemented, and I believe I screwed up this slide, but the gist is that you have an input pin, and you have a while loop watch to make sure that it's always high. And it just sits there spinning until it drops low, at which point it checks to make sure that it's low, and then it shifts in the bits and everything and checks the parity. But it will, if you already have it low by the time that it enters this, then it just falls through. It never waits on you. Now, samples are only taken at discrete points. So it just looks at the pin. Let me grab some water. So it checks it only at one moment in time, and it bases all of this timing on that single falling edge, which might not actually be a falling edge. If you make it already low and you guess at the moment at which it will start, then you can be sure not to knock its timing off, but at the same time, you can sort of guess at its timing. And by speaking slowly, by sending your bytes slowly, you're able to send lots of bytes, have little error in interpretation, and at the same time not affect timing. So the conversation will look like this. You have a SYN message from the attacker. It's 0x80. The victim will acknowledge with 0x90. Then you'll have the packets of the attack frame. This begins with a header, a command byte, then you've got lengths, you've got 4 bytes that don't matter, and after the LH is when your password begins. And you have to begin doing your weird timing with the password. You don't have to worry about the header byte or the command byte resetting timing, because nothing has occurred that's worth measuring yet. So if you think of this as a race, after you send the 4 bytes that don't matter, the AL, AH, LL, LH, then the line is high, and when you drop it low to begin sending your password, that's when the starter pistol fires. That's when you have to begin measuring timing. In RS-232, it begins listening at some point. Then, with the bit-banged implementation, you see it waits for the falling edge, and then it measures everything after that. Ideally, we would like these to line up perfectly. Instead, we drop it low early, and then we predict when it will begin listening. And then you can avoid these errors. You can avoid affecting its timing, but at the same time you can measure the result. Some other fun stuff that you can do. You can drop the voltage to the victim chip beneath the documented minimum voltage just for a bit, and then bring it right back up. And if you're lucky, on any given attempt, you do lots of attempts to get this to work, you can misexecute or skip instructions. This is a commercial device, semi-commercial, for doing that to smart cards. Satellite TV pirates use this to re-enable a smart card that's been disabled. And basically, you've just got this mux. You've got 1 voltage, then a fraction of that voltage. You drop the mux, bring it right back up. On a scope, it looks sort of like this. This is my first attempt at building one of these things. This is my business card with an LED on it and a resistor, and it runs a program that's just an infinite while loop, and then after that there's an infinite blinking loop, and the second loop should never run. But in this layout, I had a modified BSL cracker, and then I've got a voltage glitcher, and then I've got my business card. And by triggering the glitch, I can make the business card skip into the section of its code that starts blinking that LED. Now, it's not terribly useful if all you can do is light an LED, but if you look at the way that the BSL is disabled, you put the constant AA55 into memory at FFBE. It's part of flash memory. And when it starts up, early on in the BSL, it checks them. And if the two are equal, if the constant AA55 and then the contents of memory at the BSL key address, it enters an infinite while loop, the JZ plus 0 in assembly language. And the single instruction just keeps jumping to itself. But if you can skip that one instruction, then it falls through to the next instruction, which is where it would be if the programmer had intended the BSL to be active. So in doing that, you can break into a BSL that has been disabled. If I know the password, but you've turned off the BSL, I can still get into it. Another issue is that it's difficult to time the glitching if you don't know exactly when the clock pulse will hit. And the clock is only exposed if you choose to expose it. The external crystal is at 32 kilohertz, and then a PLL multiplies that frequency for the internal clock. And even then, the external crystal needn't be used. It's not powered up when the BSL is running. So instead of sharing the crystal between two or doing weird stuff like that, you can do power analysis on the board. Okay, so in this case, we're trying to find the instant in time at which a clock edge strikes. And here are some clock edges coming out of the VCC pin of the chip. If you remove the bypass capacitor, the chip still functions. But whenever a clock edge hits, that's when the chip is doing actual calculations, the voltage falls. And there's not much that they can do. There's not much that they can do about this because it's a power-efficient chip. You buy this because you want it to run on a battery until the end of time. And if they were to make it use this much power at all times, then you wouldn't get that advantage in the product. So I'm presently working on a device which extracts this clock and just gives you a digital square wave. And then you can time your glitching on that square wave. So back to the BSL cracker. I started with the first generation model, then the second generation, and now the third. I apologize for being in black and white. The only picture I had on my laptop was from the paper, which you'll find in the proceedings. These two chips on the right are both 4053 muxes, which can be used to do a voltage glitching attack on the device that you're communicating with. And at this point, all of the I/O lines are switched to high impedance so that no power can be sucked out of them. And then the voltage line drops to a lower voltage that's controlled by an I/O pin. By use of this, you can glitch past a disabled BSL. With better firmware, you should be able to glitch past the password comparison itself. If you glitch through it such that it never actually compares a byte, then it can never disable your access. And the way the code works, it first gives you access, and then it compares all of the bytes. And if any byte is wrong, it cuts out access. If 12 are right, it cuts out access 12 times. But if none of them are compared, then it never cuts out access. If only the first one is compared, then you only have to get the first one right. And this is in a loop, so falling out of the loop allows you to skip all of the rest of them without having to perform the glitch multiple times. So are there any questions?
Yeah, please use the microphone for the benefit of those who cannot be among us.
Cheers. Did you have access to the BSL source code before you started?